Hello, everyone. I'm very happy to talk about our new paper on streaming algorithms. The keywords you need to remember for this paper are streaming algorithms, multiple passes, and lower bounds. So let's see what these mean. I will be talking about streaming algorithms for graph problems. And the picture I want you to have in mind is that there is a massive graph, say all users on a social network, and we want to compute some function of this graph. Say we want to know what is the minimum cut in this graph. However, we cannot use classical algorithms to do that because this graph is the graph of all users on the network and is too big to fit inside the memory of your personal computer. So the only way you can access this graph is if you go to, say, an external data center, and then you get access to this graph as a stream of edges. This is exactly the streaming model. There is an algorithm and there is a graph. Vertex set is V, edge set is E. The algorithm knows the set of vertices. However, the set of edges is presented to it as a sequence. It can make one or more passes over the sequence, and at each pass, it gets to visit each edge one by one. When the algorithm visits an edge, then it can do an arbitrary computation using its current memory state and that edge to get to its next memory state. But when it leaves the edge, it must forget everything about it and only work with its memory state. So this will go on till the number of passes in the algorithm, and eventually the algorithm will use its memory state to compute the correct output. Now note that because we allow the algorithm to do an arbitrary computation on its memory state, if it can remember the entire sequence, then it can compute any function. And because there are only n square edges in this graph, the sequence is at most n square in length. And therefore, if you give the algorithm n square memory, it can compute any function by just remembering the entire sequence. However, we want algorithms that use much smaller memory than n squared. We want low memory algorithms for graph problems. And we also want to minimize the number of passes that the algorithms make over this sequence, because the sequence has all the edges in the graph, which is a huge number, and each pass is costly. So we typically want to minimize the number of passes down to the last constant. This is what streaming algorithms are all about. And these have been studied since the last 2 decades now. And we are now at a point where we have a very good understanding of streaming algorithms that are allowed to only take one pass over the sequence. We know very clever algorithms for various problems that we are interested in. And we also know very strong lower bounds. We know for many fundamental problems, any algorithm that solves those problems and uses one pass requires n square space, which is the worst possible, because in n square space, you can compute any function. And these problems include directed reachability. The input is a directed graph with two special vertices, S and T, and you want to know if S can reach T in the graph. Finding the shortest path in an undirected graph, finding the maximum or the minimum cut in a graph, and many other problems. However, all the lower bounds that we have for all these problems crucially rely on the fact that the algorithm can make exactly one pass over the sequence. And even if the algorithm has one extra pass, then many of these lower bounds just do not hold. For example, the minimum cut problem requires n square space with one pass. But when you give it one more pass, then you can compute it exactly with only n space. So you get a quadratic improvement with just one extra pass. If you give it some more passes, but still a constant, then you can compute a very good approximation to the maximum matching. With log n passes, you can start to compute independent sets in the graph. And all this goes to show is that if you have streaming algorithms with only a few passes, they are still much more powerful than streaming algorithms with exactly one pass. So we have some idea that these algorithms are very powerful, and they're in particular much more powerful than one-pass algorithms, but we do not have a very good understanding of the power of multi-pass streaming algorithms. And the reason that is because we do not know strong lower bounds for these problems. One specific question that we do not know is, are there problems for which even multi-pass algorithms need quadratic space, which is the worst possible? This is the question that we study in this paper, and we show that indeed there are several fundamental problems that we care about that even multipass algorithms cannot solve. And examples include ST reachability, which I just defined, a directed graph with two special vertices, S and T, and you want to know whether S can reach T. Finding shortest paths in an undirected graph, finding if a graph has a perfect matching or not. And we show that all of these different problems, along with some others, require almost quadratic n to the 2 minus little of 1 space. even with streaming algorithms that are allowed to make square root Gaussian passes. So this is the main result. It is essentially the first n-square lower bound for multipass streaming algorithms. And I'm saying essentially because of this work by Sepper, Asadi, and Ranras last year that showed us the same almost quadratic lower bound for these problems, but only for two-pass streaming algorithms. And their construction very crucially used the fact that the algorithm only has two passes, and it starts becoming easy when you give the algorithm one more pass. So this is the first instruction where you have n-square lower bounds for all the way to root Gaussian passes, and even beyond that, it degrades gracefully as you increase the number of passes. Another cool thing about this construction is that the instance that is used to show this lower bound has a very nice recursive structure. And that is very interesting because usually when you have structured instances, then a streaming algorithm can learn the structure in one pass, or in the case of AR20, two passes, and then the problem starts becoming easy. But here, we actually derive a structured instance where streaming algorithms cannot even learn the structure unless they have root Gaussian passes or n-square memory. So that's pretty interesting. As an aside, if you have random instances, then you can use ideas like Geo16, but we know for these instances, you cannot get a quadratic lower bound. It's close to linear. It's actually only slightly above linear. Okay, so that is that. We also have a different construction using the same techniques that allows us to get lower bounds for even more passes. We can push it all the way up to log n over log n passes, but the space lower bound is weaker. The space lower bound is now only slightly superlinear. It's n to the 1 plus 1 over log n. So this is our main result. And before I show you how to prove this result, I want to first spend some time on how exactly do we get the same lower bound for so many different problems? What is it that connects all these problems together? And the answer is, what we actually do is we construct what we call set hiding graphs. What are set hiding graphs? Well, fits a number n that is equal to 3, let's say. A graph that encodes a set S that is a subset of 3 is a directed layered graph that has a dedicated first layer and a last layer with n elements each. And one property that this graph satisfies is that a vertex I in the first layer can only possibly reach a vertex I in the last layer. So there is no way there is a path like the red one here, because it takes 2 in the first layer, 3 in the last layer. This path cannot exist. And moreover, vertex I in the first layer will only reach vertex I in the last layer if I is in the set. So if you want to encode the set 1, 3, then 1 will reach 1, 2 will not reach any vertex, and 3 will reach 3. So this is the graph that encodes a set 1, 3. And we say a construction of such graphs, or more precisely, a construction of distributions over such graphs, is set hiding if streaming algorithms cannot tell if those graphs are encoding the set S1 or they're encoding the set S2 for all S1 and S2. So what we shall actually do is we shall show that there are set hiding graphs for root Gaussian pass algorithms with n-square memory. And this will imply the result, because if you cannot tell any two sets apart, then in particular, you cannot tell if the element 1 is in the set or not. And therefore, you cannot tell if this vertex can reach this vertex. Now simply mark this as S, mark this as T, and you cannot tell if S can reach T, so that you cannot tell if you cannot solve directed ST reachability over a graph. Okay, and this is the lower bound for ST reachability. You can use similar simple reductions to get lower bounds for all the other problems that I claimed. You can actually get lower bounds for even more problems like matrix rank and LP feasibility, but we will not go into those. So back to set hiding graphs. In fact, we shall construct objects that are even stronger than set hiding graphs. We shall construct what I will call permutation hiding graphs that are very similar but stronger. Here, not only do you have a set S, which is a subset of n, but you also have the permutation on the first n elements. And now the property you want is vertex I in the first layer can only possibly reach vertex pi of I in the last layer. And it does that if I is in the set. So 1 is in the set, and therefore 1 reaches pi of 1, which is 2. 2 is not in the set, so 2 does not reach any vertex. And 3 is in the set, so 3 reaches pi of 3, which is 1. And again, this is how you encode a set and a permutation. I will say that the graph is permutation hiding if for any two pairs S1 pi 1 and S2 pi 2, a streaming algorithm cannot tell if the encoded set is S1 pi 1 or S2 pi 2. Okay, so hopefully I have convinced you that if I can construct perm hiding graphs, which are strictly stronger than set hiding graphs, then I have proved my main theorem. And in the rest of this talk, I will show you how to construct perm hiding graphs. This will be done in 4 steps. In the first step, I will recall, this is probably known to many of the people listening to this talk, but I'll still recall the one-pass lower bound for directed ST reachability. That says that if you want to solve ST reachability on a directed graph in one pass, then you need n square space. This will be the first step. The next step will be to use this lower bound to show that there are graphs that are weakly set hiding for one-pass algorithms. I will define what it means to be weakly set hiding when the time comes. But let's now move to step 3, where I will use these weakly set hiding graphs to get strongly set hiding graphs. These are the notions that I just defined, that you cannot distinguish two sets from each other. And in this step, I will assume that there are permutation hiding graphs. So this should raise some eyebrows because I just said that permutation hiding graphs are strictly stronger than set hiding graphs. And therefore, why is this step not trivial? The reason this is not trivial is because the number of passes is different. What I shall assume is I shall assume that there are graphs that are permutation hiding for p-pass algorithms, and I shall use them to construct graphs that are set hiding for p+1 pass algorithms. And because I add an extra pass, these two objects become incomparable and this step becomes non-trivial. So great, we can convert weak to strong assuming perm hiding graphs, but do we have perm hiding graphs in the first place? And this is the last step of the proof where I show that the weaker object, set hiding graphs, actually implies the stronger object, perm hiding graphs, with the same number of passes. So this completes the proof because you trivially have 0-pass perm hiding graphs. You apply step 3 to it and get 1-pass set hiding graphs. You then apply step 4 to get 1-pass permutation hiding graphs. Then you go back to step 3 and get 2-pass set hiding graphs. And you can repeat this root log n times because each time you apply a step, it has a blow up. And after root log n times, the blow up is so large that the graph, the lower bound starts becoming trivial. So you can do this root log n times, and eventually you have root log n pass perm hiding graphs as claimed. This is the proof outline. And now let's see how we do each of the steps. So let's start at the beginning. We want to show a one-pass lower bound for ST reachability. And for this, I want to work with a random directed bipartite graph. This graph is directed, all the edges are left to right, but I'll not show those arrows for convenience sake. But this graph is essentially a random bipartite graph where each of these two layers have n vertices each, and each edge is present with probability 1/2 independently. Now, besides these edges in the random bipartite graph, there are 2 extra edges, one of which connects S to a random vertex on this layer, and another one that connects a random vertex in this layer to T. And these edges, which correspond to layer 1 and layer 3, are presented after you see all the edges in the layer 2. So if an algorithm wants to compute ST reachability in this graph, it essentially only needs to know if this black thick edge is present or not. However, because layer 2 is presented before layers 1 and 3, it does not know which edge out of these n square edges should it remember to solve reachability. And because it does not know which edge to remember, it actually has to remember all n square edges. And therefore, to solve ST reachability in one pass, it must remember all the edges in the bipartite graph, and this is the n square lower bound. This is step 1 in our proof. I showed you how ST reachability is hard for one-pass algorithms. Now I want to generalize this argument and show that there are constructions of weakly set hiding graphs for one-pass algorithms. Let us first see what are weakly set hiding graphs. So I defined set hiding graphs as graphs that encode a set. I can only reach I if I is in the set. And I said that if it wants to be strongly set hiding, then for any two sets S1 and S2, no algorithm should be able to distinguish between the case when the encoded set is S1 and when it is S2. For weakly set hiding graphs, the requirement is much weaker. All I want from my streaming algorithm is that if it has low memory and few passes, then it should not be able to output the set correctly. It may know most of the elements in the set. It may be able to output a good approximation to it. But for the purposes of the weakly set hiding property, all I want from the algorithm is that it cannot output the set exactly. correctly. And observe that because an element I is in the set if and only if the ith vertex in the first layer can reach the ith vertex in the last layer, computing the set S exactly is basically like solving n different reachability problems on the same graph. The edge set is the same, but the sources and the sinks are different. And I just showed you that one reachability problem is hard, so it follows that n reachability problems are also hard. But turns out the argument is not that simple. And it is not simple because we need to ensure that our construction is actually encoding a set. And for that, we need to make sure that the ith vertex on the left can only possibly reach the ith vertex on the right. So in particular, there are no red edges like this because they take S3, the third source, to the second sink. And also what this means, if you take all the vertices that are connected to this first layer and all the vertices that connect to the last layer, then the induced graph formed by these vertices is actually a perfect matching. And of course, we want n square edges in the bipartite graph, so one perfect matching of size n will not suffice. We actually need the graph to have n different induced matchings in this bipartition. Are there such graphs? The answer is yes, and these graphs are what are called Rusha-Shemeredi or RS graphs, and these have exactly the property we want. There are n different induced matchings of size n, but the best constructions that we know of these graphs actually have a blow-up. If both of these vertices or layers have n vertices each, then the size of the middle layers is a factor of 2 to the root log n larger. It is n times 2 to the root log n. And it is exactly because of this blow-up of 2 to the root log n that our construction is stuck in root log n passes. We will need to apply this RS graph construction recursively for each new pass. And therefore, once we apply it for root log n passes, the blow-up becomes more than a polynomial, and the lower bound starts becoming trivial. So that's why we are stuck at root log n. But for now, this does prove that we can have weakly set hiding graphs for one-pass algorithms, and therefore this finishes step 2 of our proof. Let us go on to step 3, where I want to transform this weak set hiding property to strong set hiding property, and I can assume perm hiding graphs. How is this done? Well, let us recall the definitions. A graph is weakly set hiding if you cannot know exactly the set it encodes. If a streaming algorithm cannot know exactly the set it encodes. And it is strongly set hiding if the streaming algorithm cannot even distinguish between two different sets S1 and S2. So to go from weak set hiding graphs to strong set hiding graphs, I need some sort of a hardness amplification lemma. And I shall do that using the XOR trait. I shall use an XOR lemma, and I shall go from weak set hiding graphs to strong set hiding graphs. How do I do this? Well, instead of encoding my set as just one RS graph, I will actually take many different RS graphs and encode a set in each of them. And my final set will be the XOR of the sets in all the RS graphs. The XOR of a set, I mean that you take the indicator vector corresponding to the set and you do the bitwise XOR. So an element is in the XOR of two sets if it is in exactly one of them. Okay, so now this is what I need to do. I need to take such a graph, many such graphs, and compute the XOR of all the graphs. I will do this next, but let us first simplify the picture a bit. I will use this gray box. I'll remove all the details from it, and I'll simply denote it like this. Here, the dashed edge will denote that this element is not in the set, and the wavy line will denote that this element is in the set. And I will also drop the labels from the first and the last layers. So this is now one RS graphs, and I need to take many copies of this and compute their XOR. Now, to compute the XOR, it suffices to show that I can compute the AND, the OR, and the NOT. Indeed, if you can compute the AND, OR, and the NOT, then you can compute any function. The NOT is simple because you simply need to change which edges are a part of the matching and which are not. You just need to change which lines are dashed and which lines are solid, and that I will not go into. Let us do the AND and the OR. Let us first do the AND. To compute the AND of two sets, I claim that all you need to do is you need to place the two RS graphs side by side. Here is an example. You have this RS graph that encodes the set S1 equals 1, 3. So the second edge is not present. The second path, sorry, is not present. Here's another RS graph that encodes the set S2 equals 1, 2. The third path is not present. And I claim that the composition actually encodes the set S, which is S1 and S2, which is equal to the intersection, which is just 1. Why? Well, vertex 1 can reach vertex 1 at the end. Vertex 2 cannot because of this, and vertex 3 cannot because of this. So this overall graph does encode the set S, and in general, it encodes the AND of this set and this set. That's how you do the AND. The next step is to do the OR. And for this, instead of connecting to two graphs in a sequence, I should connect them in parallel. So now this top portion is the set S1, which is 1 and 3 again. This bottom portion is the set S2, which is 1 and 2. And I want to show that this overall graph encodes the OR, or the union of these, which is 1, 2, and 3. So I want to show that 1 can reach 1, and 2 can reach 2, and 3 can reach 3. This is indeed true. 1 can reach 1 through actually two different paths. One is this, because 1 is in both the sets. 2 can reach 2 because of this path, and 3 can reach 3 because of this path. And therefore, this graph encodes the set 1, 2, 3, and in general, it will encode the OR of all these two sets. So I showed you how to do the OR, how to do the AND, and therefore we can combine these multiple times to compute the XOR of the graphs. But this actually does not suffice to get strong set hardness. And it does not suffice for a very specific reason. There's one thing that we need to do in addition to this to get hardness. And that thing is because algorithms can attack this construction in the following way. Consider an algorithm that does not care about any of the elements in these sets except the first two. So there are n elements in this set, but I will only care about the first two elements in the set in each of the RS graphs. And because there are only n matchings in an RS graph, I can remember the first two elements of all matchings using only linear space. So in n space, I can remember the first two elements of each set directly. Now, because I know the first two elements of each set, I also know the first two elements of the XOR, or of the output set, and therefore I can distinguish between two sets that differ on these first two elements. So this is the problem. This is why this is not strongly set hiding. And the solution to make it set hiding is simple. You simply permute each of the elements in different RS graphs independently. And now, because each of these is permuted independently, there is no way you can identify which two elements correspond to each other, and this attack does not work. How do you permute them? Let us focus on one RS graphs. Again, these permutations will be applied to each RS graph independently, but we'll only look at one RS graph here. This encodes some set, but I will add to it a permutation that changes which elements are in the set and which elements are not in the set. So earlier 2 was not in the set, but now 1 will not be in the set. But to make sure that the overall graph is still consistent, I shall also apply the inverse permutation later on. So this is now a permuted RS graph, and this is indeed set hiding for one-pass algorithms, but only for one pass. If your algorithm has more than one passes, then in the first pass, it can learn these permutations. These are simple graphs with only n edges, so you can remember them. And once you know all these permutations, you can use the attack as before to break the set hiding property. So how do I go from one pass to more than one passes? Well, I do have an assumption. I know graphs that will hide my permutations for p passes. So this is what I use here. Instead of keeping these permutations as just permutations, I shall encode them using p-pass permutation hiding graphs. And now that each of these permutations is hidden using a p-pass permutation hiding graph, the overall structure I have is a set hiding graph that is hidden for p+1 passes. And with this, I finished the proof of step 3. I showed you how to construct set hiding graphs from permutation hiding graphs and add an extra pass. And what remains to be done is to show that the weaker object, set hiding graph, actually implies the stronger object, permutation hiding graphs. Let's do that. And for this, actually, let us first focus on a simple case where the permutation is just a swap. You either have elements that are not swapped or those that are swapped. And the justification for this one case is because a permutation can always be written as a sequence of swaps. So if you can encode one swap, then maybe you have a way and you can generalize it to all permutations. So for now, we will just focus on one swap. Either 1 is mapped to A and 2 is mapped to B. This is the no swap case. Or 1 is mapped to B and 2 is mapped to A. This is the swap case. And we want to hide these two cases from streaming algorithms. The first thought that comes to mind is, okay, you still have matchings on layered graphs. Why not just use RS graphs just like before? And this actually doesn't work. The reason this doesn't work is because RS graphs are only helpful when the pairs of vertices that can be connected are known. And the unknown is whether they're actually connected or not. So if it were known that 1NA and 2NB are the only pairs that can be connected, and the question is whether this edge exists or not, then you could use our set hiding construction like before and get the same hiding property. But for the permutation case, we do not even know this. You do not know if one is going to be connected to A or going to be connected to B, and therefore you cannot use RS graphs. So how do we hide this one swap? Well, the solution is to add 2 extra layers and try to transform it to a gadget where you know which pairs can be connected. And the question will be the same as before, whether the pairs are connected or not. So how do we do this? Like I said, we will add 2 extra layers. These layers will have 4 vertices each, and these vertices will correspond to all pairs of possible combinations of this and this. So you will have a vertex corresponding to 1, comma A. You will have a vertex corresponding to 1, comma B, 2, comma A, and 2, comma B. And finally, vertex 1 will be connected to all the vertices that have a 1, so 1, comma A and 1, comma B. 2 will be connected to all the vertices that have a 2, 2, comma A and 2, comma B. A will be connected to all the vertices that have an A, 1, comma A and 2, comma A. And B will be connected to all the vertices that have a B, 1, comma B and 2, comma B. These edges will always be present. These are the fixed edges. And now for the no swap case, I will additionally add these 2 edges in the graph, from 1, comma A to 1, comma A and 2, comma B to 2, comma B. And now observe that the overall graph connects 1 to A and 2 to B. So it's just like the no swap graph. For the swap case, I will add the other 2 edges. And now the overall graph connects 1 to B and 2 to A. And therefore, it's like the swap graph. And for both of these cases, I did not change which pairs of vertices are mapped. I just changed whether the edges are present or not. And therefore, I can use set hiding graphs just like before to hide this one swap from the no swap case. So this is how you hide one swap. I claim that this gadget of hiding one swap can actually be extended and applied to hide disjoint swaps over pairs that are elements of n. What do I mean by this? Consider now a permutation over n elements. It's not a swap, but it's not a general permutation either. What this permutation satisfies is that out of these n elements, I have grouped some of them into disjoint pairs. And this permutation can be obtained by either swapping or not swapping each of the pairs. So let k be the number of such pairs, then I will consider 2 to the k possible permutations that can be obtained by either keeping the vertices as is or swapping them for each of these pairs. And I claim that because these pairs are chosen to be disjoint, I can apply the gadget I had before to each of the pairs separately, and I can get a construction that hides all these 2 to the k, which is at most 2 to the n permutations from each other. But this is still not all permutations. At best, I get 2 to the n over 2 permutations that I hide from each other. How do I get all the permutations? For this, we rely on a theorem from ATS 83. This was phrased as a theorem on sorting networks. But in our language, what this means is that if you have, what this means is that there exist log n layers like this, and a selection of disjoint pairs for each of the layers, like the blue rectangles, such that any permutation on n vertices, which is the size of a layer, can be written as a combination of either swaps or no swaps for each of the blue rectangles in all the layers. So you give me any permutation on n vertices, I shall have log n layers like this, and for each layer I shall have some blue rectangles that are disjoint. There will exist a choice of swap or no swap for each of the blue rectangles, such that the overall permutation that I encode through this graph is the permutation you gave me. So now that I have this theorem, which actually comes from sorting networks, I can use my gadget to hide one swap for each of these blue rectangles. And the overall thing I will get is something that will hide the entire permutation by a simple hybrid argument. So With this, I've finished the proof of step 4. And this shows how to get strongly permutation hiding graphs from strongly set hiding graphs. Overall, because you can apply these sets recursively, this also shows how to get permutation hiding graphs for root Laurent passes. And this finishes the proof. Thank you.